Okay, today we're going to be talking about transformations of exponential functions. Now, I should probably actually get an exponential function up here. That would probably make this easier. Cool. So, exponential functions we know look like both of these curves here. We start with the black curve and we want to turn it into the orange curve here. So, our goal is to figure out what's happening here. Now, to me, this looks like we took this black curve that kind of goes up and we flipped it. So that's a reflection of some sort. And to flip it, to make it look like this orange one, that's a reflection over the x-axis. It's a horizontal, or sorry, a vertical reflection. So I've prepared some notes here. Let's go ahead and find the section here on reflections. If I'm reflecting over the x-axis, this vertical reflection that I was referring to earlier, I want to have a negative sign out in front of the function. So let's go ahead and put a negative sign there, and you'll see it'll flip over. Now, there's also something else wrong here in that we need to reflect it over the y-axis to make it face the right direction. So if we want to reflect over the y-axis, like I have down here, I want to put a negative sign in front of the x. So let's change this into a negative. And you'll see it's not perfectly lined up just yet. It looks like we have to shift this up. You see how the y-intercept of the black curve is -1 and the y-intercept up here is 5. So that means we need to go up 6 to shift something up. You'll see here I need to add something outside of the function. So let's add 6 outside the function, see what happens, and it looks perfect. Let's submit that. Cool. And then all of these problems are similar. We can try another one here. This one looks like we're going to have to reflect. So I can reflect it over the x-axis by putting a negative in front of the y. And it looks like it still looks backwards, so I'm going to reflect it over the y-axis by putting the negative here. And then it looks like I need to shift it. Let's see, I start at the y-intercept of -1, I go up to 3. So that means I need to add 4 here. And there we go. So we can use these patterns here for translations. If you want to pause here, you can. Translations are just shifts, and then reflections, I have the patterns here, if you want to pause and look there. And that's all you need for this problem. So let's focus on the next category here. We're just going to translate some functions. And perfect, it gave me an exponential. So they want us to transform this given graph by moving these blue dots here, or this green dot here, if you just want to shift things around. The blue dots are helpful if you're trying to like stretch or compress this graph, but if you look here, this is our exponential function. The function itself is here, and we've added 4 outside. So if I look over here, if I'm adding a number outside of the function, that's this case up here, this is a shift up. So we're shifting up by 4, and if I'm going to shift without stretching or compressing, I want to click on this green dot and move it up 4 dots there. So we started at a y-intercept of 1, and we went up to a y-intercept of 5. That's good. Cool. So let's try something harder here. These ones are going to be a bit spicier. Let me make sure I'm on the correct type of graph, though. This one's pretty similar to the one we did, so let's try this one here. I have an exponential, and I have a -1 outside of the exponential function. So if I'm minusing something outside of the function, that's a shift down. So we're going to go down 1. So our y-intercept goes down from 1 to 0. Okay, let's try another one here. Let's keep on looking. I'm trying to find something a bit harder. Looks like actually all of these are just going to be vertical shifts. Interesting. Okay, well, let me at least give you a different problem if we're going to do that. Let's see. We have the exponential and we have a +5. Remember, if we add outside of the function, it's a shift up. So let's move this up. We end up with a y-intercept of 6. Okay. Now, I will say, if you had something like 2 to the power of x minus 6, and the minus 6 was within the function, like within the exponent of this function, This would be either a shift to the right or to the left. If I have a minus next to the x here, like a -6 here, that's a shift to the right. So that's really a shift. If I start here, I would shift it to the right 6 units to move it over here. Okay, let's try another one here. And again, I'm going to switch just to exponential functions. That's the only thing we're focusing on today. Okay, so they give us this function. So we're going to start with that. Let me zoom out here so I can see everything at once. We want to write a function that would shift this to the right 1 unit. So let's first start by writing the original function, which is negative 2 to the power of x. To get the power, I'm going to hold shift and press the 6 key on my keyboard. We want to shift this to the right. So let's take a look at our notes here. If we're shifting to the right, that's going to be a minus whatever number it is next to the x. So that means next to this x here, I'm going to put a -1. And it needs to be inside of the exponent, which is, this is perfect here. So let's submit that. We try another one. We're shifting this down. So I'm going to start with my original function, 3 to the power of x. 3 to the power of x. And we shift it down 2, so that's going to be a -2 outside of the function. That means it's outside of the exponent here. Okay, cool. Let's try some harder ones here. Now we're going to go on to more complicated translations. Here's the exponential. Again, same deal. We're starting with our original function. I'm going to test something, see if I can copy and paste it in. You cannot copy and paste it in. You're going to have to write it in manually. To the power of x. We want to go left 1 unit. We haven't done a left transformation yet. Well, left is going to be plus something next to the x. So it's going to be left 1, so it's going to be a +1 next to the x inside that exponent there. A downshift, remember we want to do a minus on the outside of the exponential function. So that's going to be our answer there. Cool. Now, let's move on to different types of transformations here. This one is on reflections, and again, I'm just going to highlight exponentials today. Okay, so you'll notice here, they gave us the graph of 2 to the power of x, but they're asking us to graph this with a negative x as the exponent. So let's go over to our reflections here. If we have a negative on the x, let's take a look at our two options here. We have this guy and this guy. The one with the negative on the x is this guy here. So it's minus on x. And this is going to be a reflection over the y-axis. So that means we're going to flip it horizontally this way. So let's try that. The easiest way to do this would be to, at least in DeltaMath, if we're reflecting this over the y-axis, I would just choose one of these points here. So I'll take 1, 2. I'm going to flip it across the y-axis. So it's going to go to the left here and become -1, 2. You'll notice the x value has changed, but the y value has stayed the same. And this is our reflection here. So let's try another one. There are really only two variations here that you'll see because there are only two axes that we know how to reflect over. We have a negative on the outside of the function. So let's look up here. This time the negative is not on the x, the negative is outside. Oh gosh. Outside the function. And you'll notice that is a reflection over the x-axis. So it's going to flip from the top to the bottom. In this case, I would again choose just a random point. Say if I chose like 2, 4 here. If I reflect it over the x-axis, that means it needs to go from 2, +4 to 2, -4. And you'll notice this original point of 1, 2 has now flipped down to 1, -2. Same with 3, 8 has gone down to 3, -8. Okay, so let's try level 2 here. Let's see what they'll give us. Perfect. Okay. So this one's a bit funkier, right? We start with presumably 2 to the power of x, because that's what this graph is. And then we have a negative on the outside of the function. That means we're going to reflect it over the x-axis. So let's do that now. I'll take 1 comma 2 and make the 2 negative. But we also have a negative on the x term. So when we have a negative on the x, that's a reflection over the y-axis. So we need to also reflect over the y. So positive 1 comma negative 2 becomes negative 1 comma negative 2. And that's our graph. Okay, so let's try stretching and compressing. These are known as dilations in math, and this is something I haven't talked about yet here. So here are my notes on this. If you would like to pause here and take a look, you're welcome to do so. I'm going to continue and use these in practice here. Okay, so we start with, well, we should probably, let me explain how I know this original graph is 2 to the power of x. We start at 1, we go to 2, and then 4, and then 8. Each time we're multiplying by 2. And these y values, like 4, for instance, is 2 to the power of the x value. 4 is 2 to the power of 2. 8 is 2 to the power of 3, etc. And you'll see here we're multiplying that function by 1 over 8, a fraction. So let's think about what that means here. If I'm multiplying on the outside of the function, so in other words, I'm not multiplying, let me zoom in here. If I'm multiplying on the outside, so I'll say my coefficient, which is the name for that number in front, and it's outside the function. Oh, gosh, outside the function. It's going to be a vertical stretch or compression. And the value of that number, the 1 over 8, is going to tell us if it's a stretch or compression. For vertical stretches and compressions, it's going to be a stretch if the A is bigger than 1, like 2, 3, 4, and it's going to be compression if A is between 0 and 1, say like 1/2, or in this case, 1/8. This is a compression because 1/8 is between 0 and 1. So what that means here is we're going to take this and kind of compress it down vertically. We're going to make it shorter. So because it's 1 over 8, we're going to divide the y value by 8. And what I recommend doing is finding a y value that is divisible by 8. Well, I have a y value of 1, 2, 4, and 8. 8's our best bet, right? Now, if we take 8, remember we have a x value of 3, y value of 8. We're going to keep that x value of 3, but we're going to divide this y value by 8. And 8 divided by 8 gives us 1. So again, the x value stays the same. It's still 3, but the y value has gone down from 8 divided by 8 to give us 1. And you'll notice if this dotted is the original and the new black curve is the new graph, we have compressed this vertically. It's gotten shorter and wider. Okay, let's try another one here. That one's a bit similar. Let's try. Yeah, this works. Okay, so let's do our quick check here. We have 2 to the power of x. Remember, it's 2 to the power of whatever x is. So for instance, 4 is 2 to the power of 2, 2 is 2 to the power of 1. Okay, cool. And this time we're multiplying by 2 on the outside. So same deal, if we're multiplying on the outside, this is a vertical dilation of some sort. And this time we're multiplying by 2. 2 is greater than 1. So that means this is a stretch. So we're going to stretch this graph higher. It's going to become taller. No, just like it's the opposite of compressing, right? When we compress, we divided by that number. This time we're going to multiply by that number here. So let's look here. It doesn't really matter which point I use. I can use 1 comma 2. The x value is going to stay the same if we're changing it vertically. But the y value I need to multiply by 2. So my y value is 2 here. I need to multiply that by 2 to get 4. And you'll notice here my point of 2 comma 4 has now stretched up to 2 comma 8 because 4 times 2 gives us 8. Okay. There we go. That should be enough to solve this section here. Let's try some harder problems. You'll notice here, okay, this time we're multiplying by a number, but it's next to the x. So when we multiply, or when we have a coefficient on x, this is going to be a horizontal dilation. Now, you'll notice things are a bit backwards here. This happens whenever we have numbers or something inside of the parentheses. Things are backwards from what we expect. This time, when the b is bigger than 1, this is not going to be a stretch, it's going to be a compression. And likewise, when b is between 0 and 1, it's not going to be a compression, it's going to be a stretch. So let's try this here. We have a 3 on the inside. That means, well, 3 is bigger than 1, so this is going to be a horizontal compression. And horizontally, that remember that's left and right, we're going to compress it to make it thinner. So let's see what that means. For this, I'm stretching it horizontally, so I'm stretching in the x direction. So I want to find an x value that's divisible by 3. My only x value that's divisible by 3 here, that's not 0, is 3. I have 3 comma 8. So I'm going to take my x value of 3, I'm going to divide it by 3, that 3 that we have here. So 3 divided by 3 is 1. And I want to keep the y value the same. The y value is still 8, but the x value has gone from 3 to 1. And you'll notice here it's been compressed horizontally, right? We have, it's almost like we took this graph and pushed it from the left and right sides and made it thinner. So that's our answer here. Let's try another one here. I want to try to find, this is not the right problem type. Here we go. This is perfect, actually, yeah. So this time, we're multiplying the x by 1 over 3. Remember, if we have a coefficient on the x, that's a horizontal dilation. And 1/3 is between 0 and 1. So this is weirdly going to be a stretch. So if we're stretching this horizontally, that means I want to take one of my x values and multiply it by 3. So say if I use this point here, 2 comma 4, the y value stays the same, but the x value, I multiply that 2 by 3 to get an x value of 6. And you'll see this graph has stretched horizontally. It's like I, I took the graph and made it wider and shorter. Okay, let's try another one here. This one is multiple choice. Oh, nope, just kidding. I'm on the wrong section. This one is going to be a mix of different transformations. So let's see what's going on here. I'm going to start over here. I have a negative sign in front of the function. So that's a reflection of some sort. If it's outside the function, it's going to be a reflection over the x-axis. So let's do that. I take the y value and make it negative. So we've reflected it over the x, dealt with this first minus sign. This minus sign is telling us we need to reflect it over the y-axis. I'm going to take the x value and make it negative. And then final step here is we want to shift this by 1. And because we're adding it outside of the function, it's going to be a shift up 1. So we're going to shift it up 1 like that. We're going to submit this. Cool. Let's try another one. That one's too easy. That one's a bit similar to what we just did. Okay, this works. So again, we're going step by step. And if you wanted to show your work on this, you definitely could. Uh, they give us this. Sometimes if it's a really complicated transformation, it's helpful to write it out like this. So negative on the outside, this on the outside of the function. And I could check my notes up here. If I have a negative on the outside, that's a reflection over the x. And then if I have a plus on the outside here, this is a plus 5 outside of the function. This is a, based on our notes here, this is a shift up. So I would reflect it over the x-axis. So I would take this positive y and make it into a negative y. And then I would move it up 5 by clicking on this green dot and moving the green dot up 5 units. Okay, so let's see how difficult these get. Let's look for something a bit more. I'm looking for something like as weird looking as possible. Uh, yeah, this works actually. Let's do this. Um, okay. So this time we have y equals 2 times 2 to the power of x minus 5. This 2 in front, remember when we multiply the function outside the function, that's a vertical dilation. And because a is bigger than 1, our a is 2 in this case. So this is a vertical stretch. I don't see any negative signs, so I don't see any reflections. Well, I guess except for this negative sign. This negative, this minus 5 on the outside. Remember, this is a shift. If it's outside the function, it's going to be up or down. Negative means it's going to go down. So let's do this. Let's stretch it vertically. So I'm going to take like this point here, my y value of 4 and multiply it by 2 to get a y value of 8. And then I'm going to shift this down. So my y-intercept starts at 2 and I go down 5. So that means my y-intercept needs to become negative 3. Okay, let's see. This one looks weird. Let's try this. Okay, so same deal here. We have y equals negative 2 to the power of 1 half x. That negative in front of the function means we're going to reflect, oh, whoops, over the x-axis. And that 1 half next to the x. Remember, this is the horizontal case for dilations. But if it's a 1 half that's between 0 and 1, that's going to be a horizontal stretch. So it's a horizontal stretch by a factor. If I'm going to be really technical here, I would write by a factor of 2. So let's do this real quick. We reflect it over the x-axis, so that positive y value becomes a negative y value. And we're going to stretch it horizontally by a factor of 2. That means my x values need to be multiplied by 2. So for instance, this x value of 3 here, I multiply it by 2 to get an x value of 6. I want to keep that y value the same. There we go. Okay, we're getting close here. Let's try this one. Problem types. Exponential. Okay, so we need to determine this based on the graphs here. So let's look. It looks like I've reflected this to make the orange curve. I've reflected it over the y-axis because it starts by going up to the right, but now it's coming down from the left. So there's a reflection over the y-axis, meaning that x here. So let's write out what we have. Reflect over y. This is going to make this f of negative x. Remember that negative is on the x. And then after we reflect it, it looks like the y-intercept has been shifted up by 1. So that means we have a shift up by 1. That means we still have f of negative x, but if we shift it up, it's going to be plus 1. And f of negative x plus 1 is that guy there. Okay. Okay, let's try this one here. We are looking at some sort of shift here. Now, what I want you guys to pay attention to is the two asymptotes of these graphs here. You'll see our original starts with an asymptote of x equals 0 here, but we want it to eventually have an asymptote of x equals -4. We want it to really look like this, ultimately, where the asymptote is x equals -4. That means we need to shift this down by a factor of 4. So we shift it down 4 units, and then that initial shift down is gonna look like this. It's a -4 outside the function. But there's a problem. If we shift it down, that means our new y-intercept is -3, because this y-intercept up here is 1, but they want the y-intercept to actually be +4 up here. So it's a shift down, but then we have to do some other stuff. What this means is we need to shift this graph over to the left. So if we shift this red graph over to the left, it's eventually going to still have the same asymptote of x equals -4, but it's going to have the y-intercept be +4. And the way we can think about this is we know we're shifting this black graph down 4, and then we have to shift it to the left, and it eventually needs to hit the y-intercept at 4. So let's think about this backwards. If I want it to hit 4 and we shift it down 4, let's figure out where on the black graph the y-intercept, the y-axis, sorry, the y-value is 8. And if we look over here, the y-value is 8 at an x-value of 3. So that means after we shift this point down, it starts at 3, 8, shift it down 4, it becomes 3, 4. To make it touch the y-axis, we have to shift it to the left by 3. So what this really looks like, after we apply the shift to the left by 3, the shift to the left is going to be a +3 next to that x, and that's what our function should look like here. Because this is multiple choice, you don't actually need to figure out the exact details. There's only one graph here. There's only one equation here, rather, with a downshift, the -4, as well as a left shift, a +3 next to the x. So you don't really need to figure out the exact numbers if you don't want to. You can kind of just process elimination and figure out, oh, this is the one that has a downshift and a left shift. Okay, let's talk about these types of problems here. Now, we've seen these ones before where we have the domain of a function and the range, and we need to figure out the new domain and range using transformations. So let me go ahead. I can't do it that way. Let's go ahead and write out some work here. Our domain, these are the x values, remember. We start at an interval of -17 to -11 inclusive, and then range for the y values. This is an interval of 5 to 15. And what's going on here is this is a negative sign outside of the function. So this negative sign here is telling us this is a reflection over the x-axis. But let's think about what that looks like. A reflection over the x-axis, oh geez, starts here and it flips down across the x-axis. That means we're changing the y values. We're making the y values negative. So the thing here that's being affected is really the range, the y values. So what I'm going to do here is I'm going to take these two numbers and make them negative. And we have to put them in order from smallest to biggest. So really it's going to look like -15, comma, -5. And that's our new range. In this case, since that's the only transformation, and it's not affecting the x values, our domain stays the same. So our domain is still -17 to -11. The range is now negative 15 to negative 5. Okay, let's try a new one. Okay, perfect. So this one is a dilation of some sort, and the number is on the, well, here, let me not get ahead of myself here. Let's get the domain and range. Okay, so our function looks like this. Our domain starts at 20 comma 28, and our range starts at negative 5 comma 13. Okay, now this function here, that 4 is telling us it's a horizontal dilation. And remember, horizontal dilations are backwards, so this 4, even though it's bigger than 1, this is really a compression. So there's a horizontal compression. That means horizontal's x values, right? And it's compression, meaning we're going to divide. So that means we're going to divide our x values, our domain, by 4. So we divide by 4, we divide by 4, so it becomes 7. Oh my god, I can't do math. It's 5 and 8 and 7. My gosh. Sorry about that. And we got to make sure these are in order from smallest to biggest, which is coincidentally 5 to 7. That's our new domain. Our range is unaffected here. So domain is 5 comma 7, and our range is still negative 5 to 13. There we go. Okay, let's try the hardest version of this problem here. And this time they're throwing a few functions and they're also throwing some infinities at us. But this is nothing we can't handle. Um, let's see here. So g of x equals negative f of negative x and then a minus 3. Our domain starts at negative infinity to 20. And our range starts at 2 to infinity. Okay, make sure I got everything right. Cool. Now, let's break this down step by step. So, negative on the outside, this is a reflection over the x. And remember, if we're reflecting over the x, that means my y values need to become inverted. So we invert y. Now this negative here, this is a reflection over the y. And same deal, this time we're going to invert over the x-axis. If you need a visual, we start here, we reflect it over the y-axis, the x values become negative. And final step here, this minus 3 is a shift down by 3. So it's y minus 3. So let's do these in order here. Let's invert the y's first. So these become negative 2 and negative infinity. We put this smallest to biggest. Smallest is negative infinity. The biggest, in this case, is negative 2. And you'll notice I'm keeping my brackets attached to this infinity, keeping that open bracket there. And this closed bracket attached to the 2, I'm keeping that closed bracket for the negative 2. Okay, so we've inverted the y's. Let's invert the x's. This infinity becomes positive. This 20 becomes negative. And then if we swap this from smallest to biggest, close bracket on the negative 20, open bracket on the infinity. And then we want to shift down. That means we subtract 3 from y. Well, negative infinity minus 3, it's still negative infinity. But negative 2 minus 3 is negative 5. So this is our new domain here, and this is our new range here. So let's plug those in. Negative 20 to positive infinity. And then this is negative infinity to negative 5. Okay, very good. Um, hopefully this is helpful to you guys. Best of luck on this assignment, and I'll hopefully see you guys soon.